So we're going to continue where we pick it up where we left off last time. We were describing this sorting algorithm because we like sorting because it imposes an order on the arrays, and an order can be exploited, right? We've already seen that with binary search. It is going to be exponentially faster to use binary search than it is to use linear search. Unfortunately, that assumes that the array is sorted, right? So how do we go about sorting? Well, we've got a whole variety of sorting algorithms. The first one, the one that we described, is actually called selection sort. The first step is to choose the minimum element. And where do you put that? Right at the beginning. Then you go through and you choose the next element and you put that second, right? And then ... If you want to think about it inductively, at some point on the ith iteration, you've sorted 0 through I minus 1. And you need to now find the minimum among these elements here and then place that at the ith element. Right? You keep going until you get all the way down to the end and the entire thing is sorted. Now you did this last time, but let's go, or you did this in your lab yesterday, but let's go ahead and walk through it again. Now I'm going to go ahead and design this using a for loop, right? Because it's natural for each element. For int I equals 0, I is less than, now where do I go up to here? I plus plus here, right? I am doing I iterations, so I'm looking at 0 through n minus 1 and I'm finding the minimum element. Then I'm looking at 1 through n minus 1 and I'm looking for the minimum element there, ... When I get down to the very end, right, the last step, suppose that array of 0 through array sub n minus 2 is sorted. Do we need to worry about array of n minus 1, the last element? No. Why? Because if the first n minus 1 of them are sorted, the last one is already where it needs to be. So I'm going to design my outer for loop here to stop short at n minus 1. Actually n minus 2 because this is strictly less than. This would be the usual idiomatic for loop, and that's going to be fine. Right? But what are you going to do at the end? You're going to look at the last guy and you're going to say, okay, what is the minimum among this one person? Right? Oh, that's the minimum. So I will go ahead and swap it with itself. And there's really no point in doing that. So I'll stop short by one iteration here. Okay. Now what I need to do is I need to find the min among array sub I through array sub n minus 1. And to do that, I'm just going to keep track of the minimum index. Min index. I'll start that at I, because I'm going to assume that the first one that I see, that's the minimum. Then I'm going to go through the rest of them, and if I find anything that's smaller, right, then I need to update that min index. So for int, I can't use I again because I'm inside this loop, so what do I use? J, right? Why? Because it's next. Where should I start it? Where should I go up to? And how should I increment? Well, by 1, right? So if I ever find something that's smaller, array sub j is less than array sub min index, then what am I going to do? I'm going to update my min index to be j. Now, where do I start it? Should I start it at 0? Now remember that inductively thinking here, I've already sorted array 0 through array I minus 1. I need to search from I up to n minus 1. So where am I going to start my j? I could start it at I, right? But then what are you doing? You're saying, I've already found the minimum, the ith element. All right, is that less than itself? Again, you're wasting time there. So we'll go ahead and start it at plus 1. Where do I go up to? That's going to look more like your idiomatic for loop because you do need to go all the way to the end to see if the minimum actually happens to be the last one. Okay? Once you've done that, now I need to swap array sub min index and array sub I, right? Because that's how we outlined it, right? We're going to place whatever the minimum element is at array sub I. How do we swap? That's pretty easy. Temporary variable, it'll take on one of the values, array sub I, say, and then array sub I has been freed up to take on the value of array sub min index. And then we need to place the temporary value back into min index. Is equal to temp. There we go. Okay? There's selection sort. Let's go ahead and compile it and see if it works. Now, to show you what I'm about to do here, I've seeded a random number generator, and then I've taken this from, I think, Lab 7 or something like that, where it generates a random array of a given size that's provided as a command line argument. We print it out before we sort it to show you that it's random data, and then we selection sort it, and then we print it out again. Right? So GCC, everything that I just mentioned is in utils. So sort demo, there we go. And let's run it. Oops, segmentation fault. Right? Oh, why is a segmentation fault? What did I say? N needs to be read in as a command line argument. There we go. I'll just go with 10. Right? 31, 45, 84. Okay, so great. It is definitely random data here. But is it sorting? It got caught, right, in an infinite loop. So let's come back over here and troubleshoot this. Anybody see what's wrong? This is not a mistake that I meant to make to illustrate something, but it's a common mistake that we see all the time. And the first thing I always do is I go, read me the for loop. All right, let's read the outer for loop. What do you see there? You raise your hand. What did you see? I. And what do you see in the second for loop? Yep, J, I, right? So make sure that you are always using I, J in your for loops there, right? There we go, good. Right. Is it sorted? Yeah, in ascending order, right? What if I want a descending order though? Come up here to selection sort. What would I change about selection sort to make it into descending? Instead of a min, what would I be looking for? A max. And instead of strictly less than, what would I do? Strictly greater than. What if I wanted both of those things though? Cut, paste, code. Cut, paste, code. Only change one thing. In fact, the variable name doesn't really matter. All that really matters is this thing right here, right? Sound like a good approach? What would I end up having to do? Selection sort, cut, paste, descending, and greater than. Right. So let's go ahead and try it out. Does it actually work, first of all? All right. There we go. GCC this and a dot out. Oh, sorry. Did I still screwed that up? I must have undone too much. I and J. There we go. GCC and run it again. There we go. And now is it in descending order? Yes. DRY principle. Don't repeat yourself. Should I have just cut and pasted that whole thing wholesale? No. In fact, that's the second step that you did in your lab yesterday. Sorting slightly better. How did we do it slightly better? We started to take these things called comparators. All right? And I'm going to jump all the way to the end and say selection sort is actually really, really terrible. And I'm going to illustrate why here in a second, why before we go on to the actual solution. So let me go ahead and restore the actual selection sort. And when you're just doing 10, great. You can print it out and it's fine, right? What I'm going to do now is I'm going to increase the size, though. I'm to 100, 1,000, 10,000, whatever. And I don't want to print them out because that's going to take forever. Right? So I'm just going to assume that now that I've checked for it and that it is actually sorting, let's go ahead and see how efficient is this algorithm. So if I go from 10 up to 100, oh, it's fast, right? Fast, right? Blink of an eye. Can we even perceive the difference between these three runs as humans? No. But what if I go up to, say, 10,000? Okay, still not perceiving any difference. What if I go up to 100,000? Okay, now it starts to become noticeable, right? In fact, is 100,000 big data? No. Is 1,000,000 big data? No, right? Is a billion big data? What is it? Think about this. This is just a billion integers, right? So 4 bytes each, 4 billion bytes. What is that? 4 gigabytes. Is that big data? No. Your typical thumbnail drive has orders of magnitude greater memory than 1 billion, right? I wonder how long that would take, though. Okay. I don't want to actually run that because we'll find out here in a second how long it would actually take. Instead, what I'm going to do is I'm going to estimate it by using a tool. Right? And now this tool will seem familiar if you remember from the PDC modules. We'll go ahead and time our run of these things. I'll go ahead and start back down at, say, 10,000. Right? So the user time here was 0.1 seconds. We'll just round it up to 0.1 seconds. Okay? That's for 10,000. What if we went up and doubled the size to 20,000? What's your expectation? So with linear search, remember, we went from 10,000 to 20,000, or when we double the input size, we also double the time that it takes. So if that holds, then I would expect this to take what? 0.2 seconds? Okay, well, almost. Right? Let's double it again. So that was 0.26 seconds. If I double it again, it's going to be what? If it's linear. Okay, was that double? Definitely not. In fact, what kind of multiplier would you say that was? From 0.26 up to 1.13. Just take 1.13 and divide it by 0.26. What do you get? More than 4, right? So keep that in your mind. 4 times as big. What if I went up to 80,000 here? Right? 4 times as big is going to be, if the multiplier is indeed 4, I would expect this to take what? About 4 seconds, and it does. So I'm starting to see a pattern here. Why is it 4? In fact, let's go back down to 10,000, right? Get that as a baseline, 0.1 seconds, right? And let's go up to 100,000, 10 times as big. Right? What do you think the multiplier is going to end up being now? This will take about, I'll give you a preview here, almost 10 seconds. We'll just round that up to 10 seconds. That's about 100 times as slow. Now, why is that? We'll come back to that. Why is that? It's because selection sort, no, that's not what I want. Selection sort. We're not going to do the full analysis. Instead, I'm going to tell you immediately that it's about n squared comparisons on an array of size n. Now you can see that intuitively. Take a look at the code again. What am I doing? I'm running a for loop. How big am I running it? N times. I'm running an inner for loop. About how many times am I running it in the worst case? About n times. N, that's like a matrix, an n by n matrix. How big is an n by n matrix? N squared. So now let's take a look, let's understand that as far as input sizes go, right? So if I want to look at this from the perspective of doubling the input size, if I go from n up to 2n, and I'm telling you that the performance is roughly n squared, then that gives me 2n squared degraded performance. Now tell me, what is this algebraically? What happens to that square? What can you do to that square? No? We all know that math. Come on. 4n squared. In other words, hey, there's that multiplier. It's going to be 4 times as slow. Right? So let's go ahead and take a look at the other example, where we go from n up to an order of magnitude greater, 10n. Right? And we go from, our performance here, n squared becomes 10n squared, which is equal to 100n squared, about 100 times slower. In other words, it's going up by a factor of, square, right? This squared term right here. That's simple algebra, one algebraic way of looking at it, right? Now put on your CalCAD again, right? How can you quantify the growth rate of a function? If I told you that it was n squared, what tells me the growth rate of that function? The first derivative, and that's equal to what? 2n, right? Something like that, right? In other words, if you just looked at 2, it would have a constant growth rate, like a linear function. But this is no longer a linear function. This is a quadratic function. And therefore, your growth rate is linear, right? It is way worse than, say, than a linear algorithm. Unfortunately, there is no linear algorithm, right? You can actually show a mathematical proof that there are no comparison-based sorting algorithms that run better than n log n, right? So there's no linear time sorting algorithms, period. There's a non-existence proof out there. So let's come over here to Wolfram Alpha, and remember that I was about to naively run this for, what's 100,000, 1 million, 1, 2, 3, right? There we go. So remember that 10,000 or 100,000 here took 7 seconds. I'll just go ahead and get it started. Now let's go ahead and come over here to Wolfram Alpha. And if I did 1 billion, 1, 2, 3, 1, 2, 3, 1, 2, 3, and divide by 100,000, which was my baseline, that's going to be 10,000 times bigger, right? That was 10,000, right? All right. So 10,000 times bigger, but remember that the performance will end up being degraded by a square factor, right? And remember that the baseline over here was 7 seconds. So times 7 seconds. How long would this actually take on that computer over there, wherever that Amazon Web Services computer, right? That's where it's being stored. Come on, Wolfram Alpha, you're better than that. There we go. Seconds. There we go. That's 200,000 hours or 8,000 days or 22 years. Right? Acceptable? No, that's not big data. Remember, your thumbnail drives have more data than I'm trying to do over here. So let's jump immediately to the actual solution here of not writing our own sorting algorithms. In fact, I'm just going to erase them entirely, right? We don't want to write our own because we end up doing naive things like selection sort or bubble sort like you saw, right? And we never see how truly bad they are because we only ever work on small pieces of data, 10, 20, 100,000 or 1,000 things, right? So what I'm going to do is I'm going to use what's built into the language, QSort, right? Now, do you know what Q stands for? Quick, exactly. It's quick sort. Well, how much quicker? We'll talk about that here in a moment. But here it is, QSort. Let me go back to my notes over here. There we go. QSort. You have a base. That's the array that you want it sorted. Well, it's void star. In other words, it's generic. It can accept an array of integers or an array of doubles or an array of strings or whatever, right? You have NEL, which is the number of elements, right? That in C, you always have to pass that if you're going to pass an array. We also have to pass in the size of each element in bytes. Because if QSort is going to take these 4 bytes over here, an integer, and these 4 bytes over here, an integer, and swap them because they're out of order, it needs to know how many bytes to swap. If it's a double, it needs to know that these 8 bytes and these 8 bytes need to be swapped. Right? And then finally, the comparator function that we actually use to compare things with. Okay. So how do we adapt that over here for my array? Well, it's just the array. How many elements in the array? And just like our selection sort algorithm, right? Or our implementation up there. And then finally, it's a bunch of integers, so I use size of int. I don't hard code that to 4. Instead, I use that macro to tell me how many bytes each one takes. And then finally, whichever one you want to use, whichever comparator you want to use to actually sort. So this one is in ascending order. Let's make sure that it's correct first of all. So GCC this, a.out, 10 elements. 12, 69, 40, 83, ... whatever. The second one is most certainly sorted. All good? Now let's do the same experiment here where we're timing this stuff. And let's go back to 100,000. What was 100,000? Was it 7 seconds? Right? Oh, well, okay. I'm going to waste all my time actually printing stuff. So let's go ahead and not do that. But there, that's more impressive. Before it was what, 7 seconds? My implementation, my stupid implementation? And now what is it? Barely measurable. I could go up to 1 million and still be barely measurable by human standards. I could go up to 1 billion, and this will execute within this class time. In fact, it'll execute by the time I'm done explaining why it's so quick. All right? Let's come back over here and understand, first of all, how it works. Quicksort uses a divide and conquer strategy. What it does first is it chooses a pivot element, right? And how it chooses its pivot element, that really doesn't matter. We'll just go ahead and choose 42, the first one, as our pivot element. Now we call this a pivot element because what we're going to do is we're going to pivot elements around that element right there. Your pivot foot in basketball, once you've held the basketball, after 2 steps, you have to stop. That becomes your pivot foot. You can't pick it up, but you can pivot around it. So we're going to pivot these elements around it. 4 is less than 42, so I'll put it over here. 9 is less than 42, so I'll put it over here. 4 is less than 42, so I'll put it over here. Then I get to 102. That's greater than 42. So where do I put it? Over here, to the right. I'm assorting in ascending order. 36 is less than 42, so that goes over here. 10 is less than 42, so that goes over here. 2 and 0 also go to the left. Now, where do I put 42? Right in the middle there. And I put it into a box because do I ever move it again? No. Leave it alone. It's where it needs to be. Everything over here is less than 42. Everything over here is greater than 42. Sound familiar? That's what sorting is, but also binary search, right? You're looking at something in the middle and then deciding to go left or right, but not both, in order to cut it in half. Now, I have not cut this in half perfectly, but this side is already sorted. I don't need to do anything more with it. This side, I repeat, and my new pivot element will end up being 4. Right? What am I doing? I'm doing this recursively. I'm doing it recursively on this side and this side. And so 9 is greater. It ends up over here. 4 is equal, so you can break ties either way. You can put it to the left or right as long as you are being consistent about it. Right? So I'll go ahead and put 4 over here. 36 is greater, put it over here. 10 is greater, put it over here. 2 is less, 0, and then 4 gets placed right here. What else do I have to do? I have to recurse on this part and recurse on this part. But I can break this down really, really quickly, right? By putting things over here and putting things over there, right? In fact, as long as it's an even split, Quicksort will have the following average runtime: log n, right? And that is base 2 because we're all computer scientists. Everything is base 2, always. Right? How much better is that than selection sort, which was n squared? Right? Well, let's break it down first of all. If I ignore the n and the n right there, log n versus n, like one of those terms, if I just compare one of those terms, that's like binary search versus linear search. This is exponentially faster, at least in one of those terms. Okay? Let's look at it from an algebraic perspective. Right? So if I go from 2n, if I go from n to 2n, I'm doubling the input size. And if my performance is n log n, then what is my new performance going to be? It's going to be 2n log of 2n. Now, algebraically, tell me how to simplify that. Think of this as a, b. What can you do with log of a times b inside the log? I can split it up and it becomes a sum instead. 2n log of 2 plus log of n. Tell me about that term right there. It's 1. Right? So 2n, and I'm going to collect the other term over there, 2 log n plus 2n. Right? I put the lesser term second instead. This versus this, right? If you ignore this one over here. Right? Let's ignore that one for a second. How much bigger is it? It's only twice as big. Right? Now there is this additive term down here. This is why we cannot call this a linear function. Instead, we call it quasi-linear, almost linear. Because really, who cares about log terms? They're so slow growing, right? Their first derivative is actually diminishing, right? 1 over n, that it really doesn't matter. Right? Now let's take a look at some very large numbers. For example, if n were a billion, which is what I'm running in the background right now. A billion is what? 10 to the 9th, right? That means that I'm going to be doing how many operations? 10 to the 9th times log of 10 to the 9th. Why is it so fast? What happens to this exponent here? 10 to the 9th. What happens to the 9 out there? Comes out front, right? Times 9 times log of 10. Log of 10 is about 3, so I'll up that to 4, right? In other words, it's 10 to the 9th times 36, actually less than or equal to, right? So in other words, it's almost linear, and there's only this very small term as I increase the size. I'm only doing about a billion or so, 36 billion operations there. And guess what? It should already be done. Right? It did take 3 minutes and 20 seconds here or so, but it did it, right? So remember our estimate of selection sort was 22 years. Over here, 3.5 minutes, right? Which one do we do? This one right here, right? In fact, what if I went up to, I don't know, what if I went up to, what would you consider big data? Trillion elements? Or what comes after trillions? Quadrillions? Quintillions? I don't know. Divided by, we just did 10 to the 9th. So, 10 to the 9th. So if I went up to, and I'm not going to be able to do it because I can't store that much memory, but that's going to be 1 billion times slower. So 10 to the 9th times 3 point, we'll just say 5 minutes. Now that's truly big data. Millennia, right? But I mean, you're actually doing big data then, right? So this is a garbage computer. This is like a two core computer. But now think about your PDC concepts that we introduced in those modules. Right? How could you break this up so that you're farming it out to a bunch of different processors? Right? On that first iteration, or when you cut this in half, what you could do is you could take, after you've partitioned it, you could take this part and put it onto one processor. And then you could take this part and put it onto another processor. That's just with 2 processors. And you've cut it in half. What if I gave you 4? Now it's cut in 4. What if I gave you 8, 16, right? Now you are handling that big data, and that's how it's actually done, right? We've got the Holland Computing Center with supercomputers that are thousands of cores, right? And so you can cut the work down by spreading it out among different processors. Yeah, if you did it with one processor, yeah, you're looking at, what is that, 6,000 years? What would that be? Minutes, 2 years. Is there any difference between a regular millennia, which is 1,000 years, and a Gregorian millennia? There we go. No, there's not. Okay, so it's about 6,000 years. But what if you had 2 processors? 6659 divided by 2. Now you're down to only 3,000 years. What if you had 4 processors? What if you had the power of the server that we gave you, I think was 64 cores? Well, now you can do it in 100 years, right? But if I gave you, I don't know, 9,000, or I don't know how many cores there are. If I did it on a GPU, you could do this on one card. With how many cores does like a 2080 Ti have? GPU cores. Anyone? No? Okay. How many cores does a 2080 Ti have? GPU cores, that is. They're not full cores. That's why you can get so many. 540. Okay. That says 540. I don't know if that's small or not. I don't know. 540. So if I had 10 of those, 5,400, I could do it in a year. But again, this is truly big data at this point, right? You're dealing with, what did I say? Quintillion? Or I was up to quintillion, right? So yeah, you will never probably in your daily lives encounter that kind of data. Right? So quicksort, much, much, much better. How do we do it in Java? Well, we've already covered that pretty much. You have comparators, and then you have collections.sort, right? And you can do it for any type. Actually, let's come back over here and do and review this really quick. What if I had a bunch of books instead? So remember what a book looks like? It's a title, author, publish date, and rating. And then I've got this this code over here to load up a bunch of books. What was it called? Load books from CSV data. There we go. So let's load up those books. Let's forget about these integers for a second. Now let's go ahead and load up a bunch of books. Books equals, and then it's in my, I've got a copy of it in my current directory. So books.csv, and then num books. I'll just use that variable. I have to declare it though. Int num books, right? So that's going to be the number of books that I load up from that file. I think that I've got a print function here, print book. I guess we'll have to run through each one of them. For int I equals 0, I is less than num books, I plus plus, print book, books sub I, and I think it's by reference, so we will need an ampersand in front of there. Let's just make sure that this works. Oh, I need books.c. Okay. Uh-oh. Oh, book.c. There we go. All right. So there are my books again. You know, everything from Harry Potter and the Deathly Hallows all the way down to a Game of Thrones. Now I've got a bunch of, let's actually get some more practice writing comparators for other types, like you did yesterday. Yesterday was like MLB team or something like that. So if I want, of course, it's always going to return an integer here. And I can say compare book. How do you want to compare books? How do you want to sort them? By title? By author? By date? Well, let's go with title first. By title, right? Now, do I take two books, book A and book B? Is that a comparator in C? No. It's only a comparator if it follows this pattern right here. Const void star, const void star. And the reason is because qsort does not know anything about those types. It needs to pass those off to the comparator to understand those, that does understand those. So what is our first step here? Cast them as the types that you want. So I don't know anything about A, I don't know anything about B. Instead, I need to force them to become books. Book, book, book. Okay? Once I've done that, then I can make whatever logic is necessary to compare those. So if X's title, why did I use the arrow operator, by the way? Because I have a pointer, right? Is less than Y's title, Y's title, then I'll return something negative. Ugh. Is that how I compare strings in C? Nope. What do I do? No? strcmp. Right? And if that is less than 0, then I return something negative. If it's greater than 0, then I return something positive. If it's 0, then I return 0. So should I even be making an if statement here at all? No, why? What could I do? Just immediately return whatever strcmp says. There. So let's write our quicksort down here to use it for books instead. Qsort. How is it any different than QSort that I called before? Remember, here's the signature of it. It's the array that you want, the number of elements in the array, the size of each element, and then the comparator that you want to use. So the array that I want to sort is called books. There are num books in that array, and there are size of book. Right? And finally, the comparator that I want to use, what did I just call it? Compare book by title. Then we'll print it out again. Oops. Now that I'm doing string stuff, what do I need? String stuff. There we go. Let's run it. We're just going to print it out once, and then it'll sort it in order of the title, and you can see that right here. It makes no distinction for articles. You know, articles being a and the. You usually don't sort titles that way. What if I wanted it in descending order, though? I want it in descending order. That means I don't have to rewrite QSort. All I need to do is write another comparator in descending order. What's the only difference? Okay, I could say -1 times this. Why? Because positive becomes negative, negative becomes positive. What happens to 0? Stays the same. I don't even need the multiplication. I could just go ahead and subtract it. Right? In fact, I don't even need any of this stuff. I'm going to use the same trick that I used up here in the descending order and just call that other comparator because it does everything for me. But if I pass it A, B, then that's no different, right? What did I do up here? I swapped them, right? Compare, but compare B to A instead. There's these little tricks all over the place that you can use, okay? Here's some tricks that you shouldn't use. What about by rating? So I'm going to grab this up here. There we go. This is called the difference trick. So if I'm looking at, say, 4.5 and versus 5.0, right? What I could do is I could just simply return the difference of them. So return x's rating minus y's rating. There we go. And this is very common to do it. But what ends up happening here? What value do I have for 4.5 versus 5? 4.5 minus 5.0 is equal to what? Negative 0.05. What's my return value, though? An integer. So what happens to that negative 0.5? Truncated and gives you what? 0. Is a book that is rated 4.5 the same as a book that is rated 5.0? No. Don't do the difference trick. Instead, you're going to have to write it. If x's rating is less than y's rating, then return something negative. Right? Else, if x's rating is greater than y's rating, then return something positive. Else, return 0. You should generally follow that pattern too. That the last one should be the one, the equality, the 0, because if you are comparing things, you get into some trouble, some other pitfalls if you don't follow this pattern. All right. By the way, this will order it in what order? Is that descending or ascending? Let me print f. Oops, n. I want to print a gap there. Clear. And run it again. So is it an ascending or descending? Ascending. So what would I do to do in the opposite direction? Same trick that I did up here, right? And then maybe label these. This is what? This is ascending. Ascending, right? Or maybe that's usually the default anyway, so you don't need to name it. Ascending order is usually the natural ordering, okay? Here's another pitfall. Oops, I did a copy pasta. There we go. What have I done there? I'm trying to sort an array of books using a comparator for integers. This will compile. No warnings at all, in fact. In fact, if I try to turn on all warnings, it won't even, it'll find other warnings, but it will not find that issue. I wonder what will happen. Well, did it do anything? It did something. I don't know. Is it in the orders that you want with respect to rating? No. Is it in order that you want with respect to title? No. Raising Steam comes before Mort? No. So what's going on here? Well, what's going on here is that it's comparing something, but it's comparing the first 4 bytes that it sees, whatever the hell those might be, right? And those likely, what is the first in the book? What it looks like title. So it's kind of, yeah, it kind of follows that, but then it doesn't. There's probably some metadata in the background. It's looking at this book and it's looking at that book, and it's not looking at any of the pieces of data that you care about. It's just looking at the first 4 bytes and the first 4 bytes. And that's it, right? In fact, it might even be memory addresses or something like that. And so it's giving you some bad results here. We're actually lucky that we didn't get a segmentation fault. In fact, I can guarantee you that if I did the opposite, that if we tried to sort an array of integers using a comparator for books, that it would definitely result in a segmentation fault. Because it's no longer looking at these 4 bytes and these 4 bytes, it's looking at these 40 bytes and those 40 bytes, and that's going to be way bigger than the array of the integers. All right. Questions on mine? Yeah, it could be memory addresses or something. I don't know. It's bad in any case. So you have to compare apples to apples and oranges to oranges. Make sure that you're using the proper comparator for each one. Do we want to see any other comparators? Otherwise, I'll save Java for now. Actually, we don't even need to do Java. We've done Java before. We can look at it next time if you want. Otherwise, we'll go into review mode. Any other comparators for books? What about author here? Remember over in Java, what did we do for author? We use this other fancier thing here called comparable. And then we put the logic for that in the class itself. We looked at that author and this author, and we compared them by their last name and then by their first name. Right? Over here in C, what would that look like? Usually I would put these in the header file, by the way. But let's go ahead and look at it. So by author, then by title. Right? Title, there we go. Right. So how would you go about doing that? If, in fact, I'm going to put in another variable here called result. And I'm going to compare their last name first. So X's author, their last name, and Y's author, last name. Remind me why author dot, sorry. Why did I use the dot operator there? Do you remember what it looks like? So here's my book. I use the arrow operator to get to the book, but once I'm in there, the person is a regular old structure. So dot operator. Right? And I'm going to use strcmp. Now, if it knows that that author comes before that author, the second author, then I'm done. But if the result is equal to 0, that means that they have the same last name. If they have the same last name, I then need to look at the first name. First. There we go. Now, what if they have the same last name and the same first name? Because I have like 5 or 6 books here written by Frank Herbert. How are you going to break times now? If the result is still 0. Oh, by the way, why did I do an if? Why didn't I do an else if? These are not mutually exclusive. Right? I need to find a tiebreaker. This is called what's a total order. This is something called a total order. When you get to, say, 235 discrete math next semester, you'll talk about partial orders, posets, and total orders. And that's actually underlies everything with respect to searching and sorting as well. So how are you going to break this tie? I set it up here. Title, right? So I'll get title, by title rating, I shouldn't have called it title. I screwed that up. By title up here. There we go. I'll get a result of A and B. Right? What if that's still result? What if that's still not a tiebreaker? 1 doesn't matter anymore. Probably not. Frank Herbert Dune, the audiobook, maybe. I don't know. So what I'll put in here is to do. Ultimately, what you need is a natural tiebreaker. Right? Something that is guaranteed to be unique. For books, that's going to be ISBNs. For people, social security numbers. I don't know. For movies, what would it be? EIDR, I think. EIDR search. Any visual medium is going to have an EIDR, a universal media identifier, right? Right? Or a surrogate tiebreaker. A unique value that is randomly generated. And we use a tool for this called UUIDs. UUID generator. Right. There you go. Google or DuckDuckGo is giving me one. So let's go ahead and generate, I don't know, how many do you want? 100? No, I want version 4. Version 1, don't use that. Generate. There we go. Those are just random hex values that have been sent through a cryptographic hash function over and over again, such that anywhere on the planet Earth over the next 1,000 years, billions of different computers, the probability that two computers randomly generate the same UUID is infinitesimally small. Right? It's still possible. And of course, all you have, if you intentionally do it by simply just cutting and pasting and giving that to two things, obviously that's violating the use case for these things. But the algorithm that you actually run to generate these things, it's almost guaranteed that it'll never have what's called a collision. It'll never generate the same two twice, right? Because it sends it through this cryptographic ringer. It's very, very sophisticated, right? Unless there's a problem with it, you'll never see the same one over and over again. And they're very, very large too. How many bytes is that? Is that 128 bytes? I don't know. Online char counter. So each one of those is a hexadecimal. And taking out the hyphens, how many hexadecimal numbers do I have? So that's 32, so 16 bytes. 16 bytes, 2 to the 16. Actually, no, 16 bytes would be 2 to the 16 times 8 possibilities. All right, so there are a huge number of possibilities. What is that? 8 times 16 is going to be what? 128. So it's 128 bits, right? So 2 to the 128. 2 to the 128. There are that many possibilities. That's more or about the number of atoms in the universe. So that's why it's very, very unlikely that you're going to generate the same one. Oh, there's a name for that. Undecillion. Right, cool. All right, so there it is again in Java. All you're doing is creating comparators and then calling collections.sort or collections.binary search. All right, we'll continue next time with we'll just start with a review. All right. In fact, next time it'll be December 1st and the advent of code starts, so we can start doing that fun stuff.